In this episode of KubeFM, I got a chance to speak to Rohit, who's a software engineer on the traffic platform team at Databricks and also an Envoy maintainer. We dive into large-scale service-to-service communication in Kubernetes and what happens when gRPC, HTTP2, and persistent connections start pushing beyond KubeProxy's layer 4 load balancing model. Rohit explains the following points: why connection-level routing breaks down under high-throughput gRPC workloads, how Databricks built a proxy-less client-side load balancing system using XDS, why they chose power of two choices, P2C, for request-level routing, how they implemented zone-aware spillover to reduce cross-AZ traffic, and the trade-offs with headless services and service meshes. This is a technical conversation about Layer 7 load balancing, endpoint discovery, and scaling traffic systems across hundreds of services. If you're operating gRPC workloads in Kubernetes, this one's for you. This episode of KubeFM is sponsored by LearnCube. Since 2017, LearnCube has trained Kubernetes engineers all over the world with their training courses. Courses are instructor-led, 60% practical, and 40% theoretical. They're given in-person online to groups as well as individuals, and students have access to the course materials for the rest of their lives. For more information, go to learncube.com. Now, let's get into the episode with Rohit.
You're tuned in to KubeFM.
Rohit, welcome to KubeFM. What 3 emerging Kubernetes tools are you keeping an eye on?
There are so many, but if I have to pick 3, I would say Envoy Gateway. It's a Kubernetes native API gateway, which is built on top of Envoy and the Gateway API. I'm personally very close to it because I'm one of the Envoy maintainers, and I have a lot of friends who are making it or working to make it great. It standardizes ingress across the ecosystem, replaces the patchwork of ingress controllers. And I would say if you have done Envoy before, you don't want to manage all that XDS configurations by yourself. So yeah, great. If you haven't seen it, please do explore it. The other thing I'm excited about is the GPTs. So they have a Kubernetes GPT. It's really good if you have configurations which you are finding it really hard to interpret. You can go ask the help. It just like gives you an LLM interface to talk to Kubernetes. Really, really great tool. I was exploring it. I was absolutely fascinated by what it can do. And I would say third one is the open cost. Cost is becoming very important. And then each team should have visibility into what their service is costing in terms of services, namespaces, teams themselves. So I think at Databricks, we are trying to bring in that view to the people, that they can just look at the cost and they can make more aware decisions. So yeah, like I would say open cost is, again, one of the tools I would recommend.
Fantastic. Rohit, you mentioned that you work at Databricks, but can you tell us a little bit more about what you do there, your role, things like that?
Sure, yeah. So I work as a software engineer at Databricks. I am part of the traffic platform team. So my team is responsible for everything coming in and out of Databricks. So we provide the fabric for all the traffic to come in, hit the services. So I would say I'm just, if you're connecting to Databricks notebooks, running a job submission, all that traffic is going in through our systems. My job is to just get it to the right place as fast as possible and securely.
Okay. And how did you get into cloud native in the first place?
Yeah, it's a very interesting story. When I first joined Databricks early 2019, the team I was put in, the traffic team, we had efforts going on to bring in Envoy. And I'm very lucky that I got involved early in the days in those efforts. My first cloud native or open source contribution was to remove this hard coding in Envoy. So what was happening was, if you have a 404 or if you have 503, Envoy was returning a hard-coded response. But then at Databricks, the proxy that we were using before, it was written in-house in Scala. It used to return a JSON. And our clients were behaving on this or depending on this behavior because based on the error code of the JSON return, they would retry. So we wanted the same behavior from Envoy. And then it was like my first open source contribution that make that response customizable. So we can give you the same JSON that the API gateway before was returning. So yeah, I think that was my entry point to cloud native.
And in terms of the role and kind of technologies that you were working with before you got into cloud native, can you tell us more about that?
Yeah, I started my career as a backend engineer. So was mostly working on Java. And I eventually became a full stack engineer when I joined Amazon. So picked up React and a few more front-end technologies. But yeah, have mostly been a backend developer. And I would say like Java was the the premier language that I was using for years.
And it's no secret that the Kubernetes and cloud native ecosystem, moves very quickly. And on top of it, you're a maintainer. How do you stay up to date, with all the different changes that are going on? What are your go-to resources?
Yeah, I would say attending KubeCon, EnvoyCon, both as a speaker and as an attendee is amazing. It gives you a lot of information about what's going on, what are the new emerging tools. You meet a lot of awesome people. That's a great resource. I would say books, but lately I've been just like getting away from books. It's not that easy. Podcast is an amazing way. I would just download a few episodes, and then if I'm commuting or if I'm in the plane and I don't have anything to do, I would just listen to the podcast. And yeah, I just go to YouTube and then start watching videos of KubeCons or other resources out there that I have not attended in the past.
And Rohit, if you could go back in time and share one career tip with your younger self, what would it be?
I would say start contributing as early as possible. If I could just go back and tell my younger self, I would say 100% start contributing to open source earlier. It's just so important to build that DNA, and it's fascinating. You meet so many people, you make so many decisions, and you see why open source software is so great, because there are people from all these companies. They bring fresh perspective that you probably cannot get in your limited daytime job, because everybody's talking the same language. So yes, 100% start contributing to open source early.
Now, as part of our monthly content discovery, we found an article that you wrote titled Intelligent Kubernetes Load Balancing at Databricks. So we want to get into this topic a little bit more. Databricks operates at a massive scale with hundreds of services running in Kubernetes clusters. Can you set the stage for us? What does service-to-service communication look like at Databricks? And why did the default Kubernetes networking primitives start showing their limits?
Yeah, so at Databricks, within a single Kubernetes cluster, we have hundreds of stateless services communicating with each other. These aren't simple REST APIs. They are high-throughput gRPC services, powering everything from our notebooks to job scheduling to model serving. For a while, the standard Kubernetes networking stack, core DNS, and all the service discovery using KubeProxy for load balancing via IP tables, it was fine. It's elegant, it's simple. But then as we scale our traffic, we had this mixed workloads. We had REST API, we had gRPC calls, we had WebSockets. It started to fall apart. Our gRPC services use HTTP2, which means we have persistent connections. And KubeProxy picks backend once per connection, not per request. So traffic do get stuck based on the pod that it gets landed on. We couldn't trust that the load balancing is evenly distributed. And as we used to see, some pods were running really, really hot and others were running cold. So we estimated 75K per month per region bill by over provisioning the capacity. So we have to highly over provision, I would say 20-30% to all our services.
For listeners out there who might not work with gRPC daily, the article highlights that HTTP2's persistent connections create a specific problem with Kubernetes layer 4 load balancing. What exactly happens when KubeProxy makes routing decisions at the connection level rather than the request level?
Right. So let me walk you through an example. Say if your service is making a call, you would have a cluster IP address. It would be my service dot namespace. It can be default or service cluster local. Core DNS resolve that to virtual IP. The request hits the node, and KubeProxy IP table rules pick up a backend pod. It's so far so good. The problem is when the decision gets made. So KubeProxy, as you said, it operates at layer 4, the TCP connection level. So it picks the backend pod once, and then when the TCP connection gets established, it's fine because connections get recycled frequently. So for HTTP 1, it's not a problem. But then for HTTP 2, since you have a lot of requests multiplexed on the same connection, you can have long-running requests where clients are just making smaller HTTP2 requests over the same connection. So some connections which have active traffic could be very different from the connections that are idle. So that creates a mismatch. You can no longer do connection-based load balancing because you might end up choosing pods which have empty capacity versus which have a lot of capacity.
Beyond tall latency, you mentioned inefficient resource usage and limited load balancing strategies as pain points. How did these limitations manifest in practice at Databricks?
Yeah, so the most visible symptom for us was the CPU. We would see some pods running over 80%, and then others were at 20%. So it created an uneven balance. We had to throw more pods at the problem so that like we don't or we run away from the situations like this, that some of our fleet is running hot and versus some of the fleets are running cold. KubeProxy also gives you nice round robin or random load balancing. That's it. But there is no weighted routing for gradual rollouts. There is no error aware routing that some of my pods are returning errors. So let me just like pick different backends. It would just keep continuing to hit the same pods. When we measured the impact across several Databricks services, we estimated roughly like 20-30% over provisioning just to accommodate the uneven distribution. And if you multiply that across like hundreds of services that we were running, it just adds up fast.
Your team's solution was a proxy-less client-side load balancing system. This is a significant architectural shift from relying on infrastructure-level routing. What was the core insight that led you toward putting load balancing logic directly in the client?
Yeah, so I think the fundamental insight was that we needed to make routing decisions at L7, which is per request, not per connection. Because as we were talking, if you start making decisions per connection and if you stick to it, you have so many requests happening. Some connections might be overloaded as compared to the other connections. So the basic fundamental was we needed to make these decisions on L7. Layer 4 load balancer simply cannot just like look inside the HTTP or gRPC traffic and route request. The second decision was removing DNS from the picture. We have DNS caching, TTLs, tail entries, like all these were creating a lot of lag when the cluster topology changes. So yeah, like the second decision that we took was just remove the DNS and reinvent that layer. So the architecture became build a control plane that watches Kubernetes directly and push endpoint updates to clients in real time. And we were using XDS protocol for that. So the same discovery protocol that Envoy uses. Client would subscribe once and then they get streaming updates as the pod comes in.
The control plane you built, the Endpoint Discovery Service, continuously watches the Kubernetes API for changes. Can you walk us through how it works and what data it provides to clients?
Yeah. So control plane is a lightweight service that we call Endpoint Discovery Service. It's actually a pretty standard term. If you look at XDS, it's nothing but a set of discovery services, and Endpoint Discovery or EDS is used for the endpoint discovery. It will continuously watch the Kubernetes API, specifically the service and the endpoint slice. These are the two Kubernetes resources. And it maintains a live view of every backend pod that you have in the service. So it's not just the IP address though. I would say for each endpoint, we track metadata, which is like the availability zone you are in, whether it is ready or not, what shard it belongs to, what is the current health status. The metadata is what enables the smart routing strategies. We would translate all this into XDS responses, specifically this thing called cluster load assignment resource. And when a client starts up, we need to talk to the downstream services. It would just subscribe to the EDS for that service. And then from that point on, updates are pushed automatically. So if a pod scales up, the client knows within seconds that the pod has scaled up. The protocol, as I said, we use XDS, which is the standard Envoy discovery protocol. This was a deliberate choice because we wanted to be in sync with what we are doing through Envoy, because we have an API gateway all built on top of Envoy. We use pretty heavily. And then the internal RPC services, which are speaking Scala, and we just wanted everything to be in sync.
You had a strategic advantage in that Databricks services are predominantly Scala-based with a common RPC framework. How did this shared foundation influence your implementation approach? And what does the client integration actually look like?
Yeah, so as you said, Databricks has a very strategic advantage that we made this approach possible. The vast majority of our internal stack is written in Scala. Historical reasons like Spark was written in Scala, and then our internal services just like continued using Scala. They all use a common RPC framework, which is based on something called Armenia. It's another open source project. Because there was just one shared library, we could embed the service discovery and load balancing logic directly in that library. So one library change and every service get intelligent load balancing. So there is no sidecar to deploy, no config to manage per service. The client integration is transparent. When a service makes RPC call, the client library subscribe to the endpoint update from EDS, maintains a dynamic list of the healthy backends with their metadata, and makes per request routing decisions. So it completely bypasses the DNS and KubeProxy. It always have a live, accurate view of the service topology.
For the actual load balancing algorithms, you settled on power of two choices, P2C, as a default strategy. For those unfamiliar with P2C, can you explain how it works and why it proves so effective?
Yeah, P2C is beautifully simple. So when a request comes in, instead of scanning all the backends to find the least loaded one, which is like very expensive and it creates contention, you randomly pick just two. Then you send the request to whichever of those has fewer active connections or lower load. The math behind is fascinating. So the power of two choices it's a well-known result for computer science. It shows that choosing the better of two random options is exponentially better than choosing one at random. So it is, I would say in plain English, it's almost completely eliminating hotspots. And for us, the results were dramatic. We went from visibly uneven QPS across pods, some getting hammered, other idle, to near uniform distribution. The before and after charts are striking. And I would say we considered more complex algorithms, but P2C struck the right balance. Like it's simple to implement, how load overhead per request, and it just works. Like we found that keeping it simple and consistent across services was more valuable than fine-tuning it per service. We did try some fancy load balancing algorithms, but then results were, I would say, almost similar to what P2C gave us. So we just stuck with P2C.
Zone affinity routing is another strategy you support, which becomes critical for reducing cross-zone costs and latency. How does zone-aware routing work in your system, and how do you handle scenarios where a zone becomes overloaded or lacks capacity?
Yeah, so zone affinity is about minimizing the cross availability zone traffic. So in cloud environments, sending traffic across AZs costs money because you pay everything in and out, and it also adds extra latency because it's a networking hop. Our system know which zone each client and each backend pod is in. That's the part of the metadata that EDS provides. So by default, we prefer routing to backends in the same zone. But you can't just blindly pin traffic to local zones. What if a zone has like fewer pods or some pods are running like unhealthy? So we built a spillover mechanism. When the local zone can't absorb the load, maybe it's like at capacity, or if we have too many unhealthy endpoints, traffic I would say intelligently spill over to the healthy zones. So yeah, it's a balancing act between affinity preference and availability. The system will just continuously evaluate zone capacity and adjust routing and weights accordingly.
Your control plane also speaks XDS to Envoy for managing external and ingress traffic. Why was it important to have both internal clients and gateway level routing share the same sources of truth?
I would say consistency. That's the biggest reason. We wanted to design a single protocol that both Envoy and our internal clients speak. Like it just eliminates all the burden on the service team to maintain two discovery systems or two systems doing the same job. So yeah, by implementing EDS and speaking the same XCS protocol to both RPC as well as Envoy, we ensured that our internal service-to-service traffic and external traffic sees the exact same endpoint data. We just have a single source of truth. And I would say as an Envoy maintainer, this was a natural choice. We also want to contribute back and make XDS better. So if we found any bugs or anything, we could just contribute back.
Now, let's talk a little bit about results. After rolling this out, what improvements did you observe in request distribution, latency profiles, and resource efficiency?
I would say the biggest thing we noticed is uniform distribution. That was the most visible change for like how QPS distribution changed. So before EDS, if you look at the dashboard for a service, you would see jagged, uneven request rates across pods. But then after we rolled out the endpoint discovery, it's just a flat line. You have all the same RPC load over the fleet. Like the pods could be 20, 30, 40 pods, 50 pods. We were seeing the exact same load. The other big one was latency. The P90 latency for us became stable and more predictable. The long tail behavior that we used to see before, it was gone. Some requests prior to EDS were taking 10x longer because something bad happened to the pod. You would just get stuck, and we would keep sending traffic to that. It went away. Efficiency. So as we mentioned before, we were over provisioning because there was uneven load balancing. We started, like, our fleets are pretty balanced now. We don't do any over provisioning. We trust the load balancing, and we trust like how EDS would behave if you have more traffic coming in. We have HPA, so you would just auto scale. And I would emphasize, these aren't just synthetic benchmarks. The system has been running for Databricks for like last 3 years. And these are real production numbers for services that are handling like literally millions of requests.
The rollout wasn't without challenges. You discovered that server cold starts became a bigger issue once client-side load balancing was enabled. What was happening there, and how did you address it?
Yeah, this was actually an unexpected consequence that also surprised us. So before EDS, with the long-lived connections, new pods would barely receive any traffic because existing connections would be stuck to existing pods. And then pods had plenty of time to warm up, fill caches, initialize connection pools. But once we switched to per routing, per request load balancing, new pods started to get traffic almost immediately after we become ready. And ready in Kubernetes terms doesn't mean fully warmed up. We just start seeing elevated error rates from pods that were like still warming up their caches or still establishing connections. We solved it in two ways. First, there is a slow start. So you do a slow start ramp up where new pods get gradual increase in traffic over a configurable window, say like 5 minutes. And second thing we did, we biased traffic away from the pods that were showing higher error rates. So if a cold start pod would return errors, the load balancing would just pick other healthy pods. And this also reinforced the need for a dedicated warm-up framework, proactive warming up services before they enter the load balancing pool.
You also experimented with metrics-based routing using signals like CPU usage, but ultimately moved away from it. What made that approach unreliable?
Yeah, we had this attractive idea. What if we could route based on real-time CPU? Send requests to least loaded pods as we measure by actual resource consumption. It sounded great in theory, but then it fell apart in practice. The core problem was the monitoring systems. So we have like different SLOs that serve for the serving workloads. Prometheus scrape interval might be 15 or 30 seconds, but in 30 seconds, a pod load can change dramatically. So CPU metrics, I would say, are trailing indicators. They are not real-time signals. By the time we see high CPU in metrics, we might already be recovering. By the time we route away from it, we might already be creating oscillation, everyone routing away, the pod goes idle, then everybody route back. So we learned to rely on signals that are directly observable in the request path, connection count, error rates, response latency, rather than the infrastructure metrics that are sampled on a different cadence.
Before settling on client-side load balancing, you evaluated alternatives like headless services and service measures like Istio. What were the key limitations you found with headless services?
Yeah, so headless services gives you direct pod IPs via DNS instead of cluster IP. So I would say that's a step in the right direction because clients can see the individual pod IPs. But in practice, there are like a couple of things that held us back. First, there is no endpoint weights. So with headless service, every pod is like equal in the eye of DNS. So you can't say this pod is warming up, give it less traffic, or this pod has higher capacity, give it more. Second thing is DNS caching. It creates staleness. So client cache DNS responses sometimes very aggressively. So a pod becomes unhealthy and get removed from the endpoint list, but client keeps sending traffic to it because your TTL for DNS is say like it's 30 seconds. So I would say in a fast-moving environment with frequent deployments, this causes real problems. And then the third thing we saw was, which was actually a deal breaker, the DNS records carry no metadata. So they're just IP addresses, right? You can't encode which zone the pod is in or which shard it belongs to or what is the health status. And without that metadata, the zone-aware routing and topology-aware strategies are almost impossible.
Istio and service meshes offer powerful layer 7 features, but you decided against them. What factors made the sidecar-based approach unsuitable for Databricks' environment?
Yeah, so Istio is really powerful and might be a right choice for many organizations, but it wasn't right choice for Databricks at that time. And let me explain a little bit more. So first thing is operational complexity. Istio injects an Envoy sidecar into every pod. At our scale, hundreds of services, thousands of pods. That means managing thousands of sidecars. The traffic team here is really small, and as a small infrastructure team, that operational burden was impossible. Second thing, the performance overhead. Each sidecar adds some CPU, some memory cost per pod, latency for every request that has to traverse the proxy. At our throughput level, it all adds up. The third thing is the specific to environment, I would say. Like Databricks already has proprietary systems for things like certificate distribution, MTLS, and bringing in Istio means we just reinvent all those pieces through Istio because Istio has like a very different way of how it does certificate provisioning, certificate distribution, and everything. And I would say, like most importantly, our environment is very heavily Scala based. It's not like we have some proxies running and then some services are Scala. It's like say 95% Scala. So in that strategy, it's just like you're attaching a sidecar to every single service. So yeah, I think one advantage for this sidecar meshes is like language agnostic, but in this case, we wouldn't have been benefited because 95% is already Scala.
Looking ahead, you mentioned cross-cluster and cross-region load balancing as an area of exploration. What challenges does extending this system beyond a single cluster introduce?
Yeah, so today our systems operate within a single Kubernetes cluster, but Databricks manages thousands of clusters across multiple regions globally. So the natural next step for us is extending intelligent load balancing beyond cluster boundaries. We are already exploring flat L3 network across clusters, multi-region EDS deployments. So a client in one cloud cluster can discover and route to endpoints in another cluster with the same zone-aware and health-aware strategies. The challenges, I would say, are non-trivial. Latencies between region means we need more sophisticated failover logic. Network partitions become like a real concern for us. And then the state synchronization problem also gets much harder. We are also looking at more advanced load balancing strategies for AI workloads, weighted routing, intelligent scheduling to handle the unique resource demands for some of the model training and inference. So yeah, the goal for us is a robust cross-cluster traffic management, which is fault-tolerant and globally efficient resource utilization.
For teams facing similar challenges with gRPC and persistent connections in Kubernetes, what key lessons or advice would you share from this journey?
Yeah, I would say understand the layer mismatch. So if you're running a gRPC or any protocol with persistent connections on Kubernetes, L4 load balancing fundamentally cannot solve your problem. You need L7 per request decision. So don't fight it. You have to embrace it. You should start simple. Like P2C is a surprisingly effective choice. Don't over-engineer your first load balancing strategy. Get the architecture right, real-time service discovery, per request routing, and start with a simple algorithm. You can always like sophisticate and engineer it from there if you want. Consistency over customization. So we found that keeping the same strategy across most services was more valuable than fine-tuning per service. So consistency also makes debugging easier and reduce operational surface area. You can validate with the real data, run simulations, compare before-after metrics. We validated that load was evenly distributed and the tail latency, error rates, and cross-zone cost stayed within target thresholds. And yeah, consider your language ecosystem. If you're using one language, just like Databricks across your environments and a shared framework, client-side load balancing is incredibly effective.
Rohit, what's next for you?
So I would say on Databricks side, I'm pushing forward on cross-cluster load balancing and building out a dedicated Envoy team. We are also exploring how to optimize traffic routing for AI workloads. The request patterns for model surveying are very different from the traditional microservices. And on the Envoy side, I'm excited about something called dynamic modules. It's a new technology that we have been working with a few companies. It makes Envoy extensible with native Rust code without recompiling. I'm also co-hosting EnvoyCon in 2026. It's upcoming. And personally, I'm just excited to contribute more and more to Envoy and Envoy Gateway.
And if people want to contribute to Envoy, or if they'd like to get in touch with you to speak about this more in detail, what's the best way to do that?
You can find me on LinkedIn. I can share my GitHub handle as well. My email is my first name dot last name at databricks.com. And I'm always happy to chat about Envoy, load balancing, networking infrastructure. So yeah, please feel free to reach out to me.
I can say it definitely worked in our case. Rohit, this is your first podcast. It looks like you've been doing this for years. So keep up the amazing work. It was great talking to you. I hope our paths cross again in the future. And if not, see you at EnvoyCon. Take care. We'll speak soon. Cheers.
Thank you so much, Bart. Thank you so much for having me.
You're tuned in to KubeFM.